All right, so welcome back to this YouTube channel. So in the last video, we have derived some of the equations, for the back propagation process in a neural network, right? So we have discussed about how a neuron can update its weights, and we have also discussed about you know the the passing of gradient, right? So each neuron is going to calculate the gradient of the neuron's input with respect to the error. So we have also calculated how that progresses, and therefore it got the name back propagation, right? So these are the equations we have derived in the last video, and as the title says, we are going to program or create a neural network from scratch without using any pre-programmed libraries. So we are going to do it since like using basic Python. We are going to code this neural network. So first, let's see, like these are the equations. So we are going to calculate the gradient of w with respect to error, which is equal to this formula. When we have this formula for the gradient of b with respect to error, and we also have the error, the gradient of the neurons input with respect to the error, because we are going to send this gradient, right? This value we are going to send it to the before neuron, so that it can calculate and update its weights, and this process is going to be happening for every neuron, right? So let's build this, and yeah. So first, but today's video we will not code this neural network on Google Colab, because we are building a neural network, right? So we just want every, like, all the code in uh, like one place, just to make sure it is easier for you to understand. You can also use Google Colab, no problems for that, but I'll just use a new code editor here, just to make you aware of you know like normal Python editors, right? Rather than only using Google Colab for all of your work for scripting purposes, we are going to use some normal Python editors. So this is a website called replit.com, or it is replit.com, right? So it is, the spelling is replit.com. All right, just go through that. You can just log in, and then click on this option, create REPL, right? Choose Python, right? Name your file. It's a neural network from scratch, anything like that, and just create the new Python file, right? And yeah, after some seconds, you'll get this beautiful Python editor, right? So you write your code here, and then you can see the result of your code here. Then yeah. So we have this editor. This is our editor. So let's code this neural network. Let's program this neural network. I will start coding, and you can understand. I'll explain. I'll take some breaks. I'll explain what is going on, what and what, and we'll be doing some new things also, and let's go. Let's hopefully you'll understand this. These are not some rocket science. You can easily understand this, right? First, we are going to import a library. So this library is called NumPy. So what is happening is, we are going for calculations such as matrix multiplication. When you want to multiply two matrices means collection of numbers, right? So you should, like, you can learn about linear algebra. I'll probably put the link in the description of linear algebra playlist. So you can have this library called NumPy. So this NumPy, what it helps you to do is, whenever you are working with matrices, right? So anything related to matrix multiplication, matrix algebra, anything, you use this NumPy. Yes, that's it. This is the, uh, like, this is the only library we'll be using. And now let's do something. I'm going to build a class. I'll just tell you what is a class. first I'm going to write the code. Well, I'm going to write the syntax, input shape and output shape, right? So this is a class is nothing but, it's just a collection of functions. So functions are mathematical, no, like functions are blocks of code that can perform an operation, right? Like if you are familiar with mathematics, like any type, you should be comfortable with functions. So functions are nothing but, a group of statements that perform a specific task. And we can group these functions into, like let's say you have multiple number of functions, and each function collectively are working on, let's say, one problem. You can just group this all functions into something called a class, right? So you can just create objects of this class, and then you can use any function inside of this class. So let's just do it. So first, like before writing any type of functions, you should create a function called init function. This is just initialization function. That is, it helps you to like initialize the class, right? And then what this initialize function takes is that whenever you are calling this function dense, whatever you have to input the function, input to the object of the class should be entered here, right? So whenever you are calling the class dense, you should input the input shape and the output shape, right? So here the input shape is nothing but the input, like the number of inputs the model has to take. Like in a neural network, the model takes a number of inputs and produces one input for now, right? So the model produces one input, like in neural networks for now. So we are going to see like how many number of inputs are there will be the input shape, and output shape will be how many number of neurons are going to be there in the current layer, right? So like what we are doing is we are just in creating layers. That's output shape is the number of neurons, and input shape is the number of inputs. Output shape is the number of neurons in the current layer. And then what we are going to do is we are going to I'll just write it up. Output shape, right? Wait a minute. There's something error here. Okay, so yeah, before you create a initialization class, you should first create self here. You should just add another variable self. What the self helps you to do is, just like you can use all of these variables inside of this class. So you are just initializing different variables such that you can use these variables in different functions, right? Okay, so what I'm doing is I'm just initializing this input shape. This is a variable of input shape that is entered by the user, or we will enter it below. So what we are going to do is we are just going to initialize this variable such that we can use these variables in our future use in different future use in different functions. So what are we going to do? What are the functions of a dense layer? Well, you know it: forward propagation and the backward propagation, right? So I'll just create a new function. So to create a function, you should use this keyword def, and then you can write the function name, and then in brackets you should write the inputs of the function, right? So these are both the inputs of the function, right? Now you can create a new function, forward prop or forward, right? Anything. And then what is the requirement for the forward propagation? Well, you need the, right, and right, there is another thing that we have forgotten to do. We should initialize the weight and biases, right? So weights are nothing but the value internal relations that are stored in each neuron. So we just initialize these weights. So let's say self dot weights. We can also delete these statements because we'll only use these statements in this initialization function. So I'm just going to say self dot weights is equal to np dot. Okay, so yeah, So we are going to create weights, right? So we are going to create weights that will be used in the following two functions: forward propagation and backward propagation. So what we are going to do, self dot weight is equal to self dot np dot random numpy dot random dot ran n, right? So what is this function is, this is what this function does is it creates some random numbers, and the input of the function is the size of this function, right? So the size is output shape by, right? So the size of the function is output shape by input shape, right? So the size of this weight matrix is output shape by input shape. That is uh, the number of neurons here and the each number of neuron. So we're just going to create random numbers in this shape, output shape by input shape, and then bias, self dot bias equal to np dot random dot random in the shape of output shape, right? In one. So bias, as we are not doing any type of matrix multiplication, we just have to have it in output shape, such that we could add bias to this, to the product of weights and inputs, right? So now we can write this function forward, right? So what are the inputs to this forward function? Well, it's just, right, I can just type in input here. Let's say we just get the input and we have to perform the calculation of neuron. So forward is, it is pretty straightforward, it, right? You just, what you will do, well, you'll just return self dot weights, np dot dot self dot weights. Wait a minute. Okay, I just have to initialize that. So we'll just have a multiplication between self dot weights and um, inputs, inputs, input, and I'll add the bias. There's an error. Okay, so I'll just forgot to write that self here. So any number of functions you wrote in this class, you have to have this self variable, right, as the first parameter. Okay, so what will return in forward function? Well, we'll just return the product of self dot weights and input, and we'll add the bias. And the main thing to remember is we should initialize the variable, right? Because we have to use this input in the backward propagation function also. So we have to write this line, self dot input equal to input, and then we can just return this equation, that is the product of self dot weights, the product of this weight matrices. Now it is random. After updation, it will change, this weight matrix will change such that we can able to find the relation between this input and the output. And then what we are going to do is we're just going to multiply the weights and the input, and we are going to add the bias. So that is forward propagation method, it. Now we get to the backward method. And then what is the input? We're taking gradient, right? So as I've told you in the last video, each neuron is going to get gradient from its after neuron. So back propagation goes from the back, right? So we are going to get update each gradient from the back, right? So from the output layer to the input layer, we are going to calculate gradient, and we are going to update the weight. So as this loop is going to go on, right? So as this loop is going to go on, each layer, and so if this layer has finished it updation, this layer will send gradient to this layer before layer, and then hopefully it will happen to all layers. So the current layer will get grad as input. Gradient is nothing but the gradient of um, the gradient of this neurons output with respect to the error. We'll get that as the input. So what we'll do now is um, we'll do the calculation, right? So we have these equations now. First, we'll calculate the derivative of w with respect to error. What is that? That is equal to grad into x. transpose. So we'll just say W gradient equals np dot dot of, what is it, grad and, this problem. Okay, so grad and x dot transpose. What is x? Inputs, right? So we'll just say self dot input dot t. So hope you understand what is going on here. Okay, so we are just going to calculate W gradient. This is nothing but, as we have saw here, it is just gradient that will receive uh, for every layer, and then we are going to multiply that by the self dot input dot transpose. And then what we are going to do, let's calculate, and we don't have to calculate B gradient, it is just grad, right? Easy. Now let's update our weights, right? So let's say self dot weights equal to self dot weights minus, yeah, we'll also going to take learning rate here. Let's just take a learning rate. Learning rate, I've talked about learning rate in the past video, so just check out the videos. Learning rate defines how fast the learning should happen, right? So we'll just take in the learning rate also, and we're just going to say learning rate multiplied by what? W gradient, right? And then we are going to do the same to the bias. Self dot bias equal to self dot bias minus learning rate, sorry, learning rate multiplied by B gradient. Right, you understand that, right? What we are going to do is we are just updating each weight, right? So we are just subtracting the learning rate times the gradient or the slope. And then what should we do? We should return the um, return the gradient of the gradient of the neurons input with respect to the error. So for that, what is the formula? We'll just multiply the gradient with the weight matrix. So we can just return, what is it, np dot dot, right? We can just return derivative of the grad and the self dot weights dot t dot transpose, right? So that's it. This is the dense function. This is the like the main part in the project that we are going to solve. So this is the layer initialization. This is the part where you develop all the forward and backward propagation. It is fairly simple, hope you can understand that, right? Just read through the code, right? uh right, yeah, that's it. This is the main part of this code, and now start to let's get started, to implement uh the next feature. So the next thing we should build is the loss function, right? So we should build a loss function. Why is this loss function? Well, right, so as I've told you, we have layers, right? Let's draw it very fastly. So let's say this is a layer, not a neuron. Let's say this layer, each layer has many neurons, n number of neurons. So what will happen is, this is the output layer, right? So what should we have? What should we do? We should give this output layer with the, what should we give the output layer? D of y by d of e by y, right? D of e by y. So, like as I said, every neuron, every layer should get this input, right? What should they get? The derivative of y with respect to the error. So what will the last layer get? Well, it will directly get the derivative of error with derivative of error with respect to y. So how can we calculate it? Let's see. So first, we have the loss function. The loss function is MSE. I think I've talked about this, mean squared error. So it is just a very straightforward. We'll just have y minus y hat whole squared and we'll get the average. That is, like I'll just do something like equal I 0 m I I, right, divided by m. So what, this is just average of the difference between I, the actual value. So here yi is the actual value and y hat I is the predictor value, right? So the y hat I is the prediction, right, of the last layer. What we are going to do is we are just going to square the difference between the actual and the predicted value, and we are going to get the average. So what is the derivative is, we can just simply do something like 2 into y I minus y hat, sorry, so y minus, let's say something like y hat I, y hat, you know, divided by m. So just straightforward. What I have talked about this, I have talked about this rule in the last video, right? So this is called the power rule in calculus. So what you will do is you can just get this uh, exponent and this, and just put it in, put it before it, and subtract one, which is here is going to be 1. So yeah, it is 2 into y minus y hat divided by m. So that is the loss function. That is a derivative of the loss function, and this is the loss function. Let's implement both of these functions. So I can just say msc, and what should be the input, yn, y true, or I can just say y pred and y true. So here y pred is the prediction of the model and y true is the actual value. And then we can just do something like, we can just return np dot mean of uh, uh np dot mean of, okay, so we can just get the mean of the power of what is the value, y true minus y pred minus y true, and we're just going to square it, right? Yeah. So what is happening is we're just subtracting y pred minus y true, and we're going to square this value and finally get the average. And then we're just going to return the value. And then now let's build the MSC gradient function, where we are going to get the gradient. So here also we are going to take y pred and y true, because we have to give the neuron the actual value, right? So we are just going to do that. And then what is the derivative, right? So what is the derivative, as I have talked earlier, it is 2 into y minus y hat, right? So what is it, it is 2 into y minus y hat divided by that, the size here, m is the size of this, size of y. So I'm just going to return something like, uh right, so I'm just going to 2 into y pred minus y true divided by mp dot size of y true, or y pred, right? So I'm just going to subtract y pred minus y true, multiply that by 2, and I'm just going to divide by y true, right? Hope you understand what is going on here. We're just going to calculate the, get the derivative for the last neuron. And then what should we do? Well, we have implemented the loss function, we have implemented the layer, like the dense layer. Now let's build a model, right? So let's just create a network. So to create it, we can just create a list of 2 items. I've talked about list in the Python basics, right? So I'm just going to create 2 objects of the class of dense, right? So let's say, first let's create the input. Let's create some random input. I'm just going to say x is equal to np.array of, let's say, range 10. All right, so I'm just going to get the first 10 numbers, and I'm just going to create an numpy array. And let's do something simple for now. Let's do something simple as y. Let's just say x into 10 plus 0.5, something like that. Let's just do, I'm just doing something simple here. And then yeah, like there is like straightforward relation between x and y, but it is hard for computer. Like it is just magic for a computer to identify this function. So the goal of computer is just to identify this function, right? Like, okay, that is the basic idea of deep learning, right? Now what we're going to do is we're just going to develop the network as a list of two items, two objects of the class gens. So I'm just going to create this class gens, and the input the input size. So what are the inputs? Input shape and output shape. The input shape is only one, because there is only one input at each timestamp, right? So at each row we are only going to have one input, right? Either 0, 1, 2, 3, etc. And then what is the output value? We can just put anything. Let's say we can add two neurons for this layer. Okay. And what I'm going to do next is I'm going to add two neurons, and like I'm just going to add like see, this layer has two neurons. That means two outputs will be emitted from this layer, and then this layer's input will be two, because like this layer's input is this layer's output, right? So therefore we are going to have two here as the input shape, and we are going to have one neuron, because the output is one number. And then what we are going to do, we have built a network, and yeah, let's just do it. Let's just go through this network. Let's implement the training process now. Okay, so I'll just say, so let's first initialize some variables. Let's say number of epochs, number of iterations. We should update these weights. Let's say I'm going to say 100. And then let's say set the learning rate. You can set any number. I'm just going to set 0.1. Like it's a magic number. And then let's start the training loop. So what I'm going to do is I'm going to say for I in epochs, or range of epochs, I'm just going to create a for loop. And then what I'm going to do is, at every epoch, what should I do? Well, I'm just going to write the code first. So what is this zip function is, like we have row column data, right? So what this zip function does is, it is just going to get us the uh, values of each row. So we have x and y's, right? So we are going to get this small x and small y as the values of each row. Okay. And then what we are going to do is, let's implement the network, right? So what I'm going to do is I'm just going to first implement the forward propagation. Like, okay, so I'm just going to say output equals x. So here we are just going to go through this network, right? So the first input, or the first input of this first layer will be x, and then I'm just going to implement the forward propagation. I'm going to say for layer in network. So I'm going to go through each layer of this network, dense, or both of these dense layers. And what I'm going to do is I'm just going to do the forward propagation. I'm just going to say here we have this forward method, right? So we have called this class here inside network, and we are going to loop through this network, and we are going to call the forward method for forward propagation. We're going to say layer dot forward on output. I'm just going to output equal to layer dot forward, because we have to give the gradient, right? So the not the gradient, we have to give the, right? So each neuron's output is the input of the next layer's neurons, right? So what are we going to do? We are going to carry out this output. We are going to change this output through this layer, right? So we are going to get this output through the layer, and then we are going to get the new layer, and then we are going to repeat this process until we get the final output. So now we'll get the final output. Let's calculate the error. Right. So I'm just going to say error is equal to, so let's just initialize error here. Right. So I'm just going to add error equal to error plus MSC, right? Wipe bread. Why? What is a wipe bread output? And what is y? Actual y? Y. Right. So I'm just going to input the predicted output and the actual output, and I'm going to add the error, right? And then what should we do? Let's do the back propagation method. right? So we have just accomplished the forward propagation. Now let's attempt the back propagation method. Okay, so let's again go through the network, but in reverse format. Okay, I'm just going to use this function called reverse. Reverse is nothing but we are going to go from back, as I've told you in the last video and the video before that. In back propagation, we are going to propagate through the network from the um, like in a reverse manner. Right, so we are going to go through this network in a reverse manner. And what are the inputs? What is the input for the backward function that we have defined? Well, gradient and learning rate. So we have learning rate here, we have this learning rate here. And what is the gradient? As I've told you just now, the gradient is nothing but the output of this function msc grad. So we are just going to get this value and input it through the backward layer, and we are going to carry out a for loop such that we do it number of times, right? So we already have these iterations, right? So this is the number of times we are going to update this neurons. I'm just going to say grad. So first let's initialize grad here for the last layer. I'm just going to say msc grad. What is the function name? Msc grad. And then what is the y pred here? What is the prediction value output? And what is the y true? Actual value, or actual value is y. And then I'm going to, sorry, and then I'm going to propagate this grad through the network and going to change it. And hopefully at each step, we are going to update this internal weights of each layer, right? So I'm just going to say grad equal to layer dot backward. And then what is the inputs? Grad. And what is the learning rate? I've initialized the variable there. That's I'm going to input the learning rate here. And then hopefully we'll just get the we'll just update these neurons, update the weights. That is the most important thing. We don't have any use with this variable grad. We just use this variable grad for calculating the gradient of w and b with respect to error, of course. And then and then that's it, right? So we are going to calculate, go through forward propagation, and then we are going to calculate error, and based on that error we are going to update each of this weights of every layer. And that's it. This is the training process, and it is over. And then what we can do is we can just print the output at each step. Let's just print the output just so I can see what is like how the output looks. And that's it. Let's just run it. Hopefully we have no errors, hopefully. Yeah, so there is an error here. Value shapes 1 1 and 2 1 are not aligned. Okay, so where is the line? Line number 42, we have an error. Backward grad and learning rate. Okay. What is the error? Line 15 backward. Okay. Okay, so grad is okay. Okay, so there is a all right. So there is a misconception, or there is a difference in the weights here. So like we are multiplying gradient and self dot weights, right? So I think there is a different shapes. Like both of these values are of different shape, I think. um what is the problem? Let's see. Like what is the shape of this gradient? Okay, so yeah, so I just made some changes here. I just made some changes in the code, and no, in the description I'll send you the before and after version, and in the next video I'll explain what I did to solve the error, what the error is. So my computer is it's slowing now, so I'll just go through fastly what I did. So yeah, like we have calculated the forward and the backward, right? So I just reduce the number of variables here, because building a neural network, like you have to do, like there will be a lot of matrices and a lot of matrix multiplication happening. So we should reduce the number of matrix multiplications as much as possible to increase the um to accelerate the process of training. So like to for seeing purposes, I just added this print statement, in which at each epoch we are going to, right, at each epoch we are going to print the error. So at each epoch we are going to calculate the error, we are going to divide it by 10, because like we are going to add the error for all, like for all of these values. So we are going to get the combined error of like all of the rows of the data set. We are going to divide it by 10, just to make sure that we'll get the average value, and then we'll print the error. So if we run it, so uh, this is the input and function, um pretty easy mapping between the x and y's. And if you run it, the training happens. So here these values are nothing but the outputs, and this is the epoch number. So it might just take some time. Yeah, 100 epochs finished. And then the error is, wow, it is just 0.06. So like let's see the starting error. What is the starting error? Okay, it started off by, like the difference is, it started off by 709, and it steadily increased to 0.06. So there has been some really good training here happening here. So like the error really converged. That is a very good sign that our model is performing very good. And if we compare it, well, here in this, let's just compare it now. Let's see. Okay, so for the first value, the input is 0, right? So we have the input is 0, and this is the function x into 5 plus 0.5. So what is 0 into 5? 0 plus 0.5. 0.5, so, right? The actual value is 0.5. The model predicts 0.9. Well, not a problem. And then for the second value, what is the x? X is at 1. 1 into 5 plus 0.5, 5.5. 5.8 is predicted. So model does have a little bit of idea of the mapping. And if you see, like the predictions are almost they are almost very close. So yeah, congratulations, you have built your first neural network from scratch. And then in the next video, we'll just try to look at TensorFlow version. Like using TensorFlow, you can easily build sophisticated neural networks from scratch. So thank you for watching, and yeah, see you in the next video.